Okay, I suppose we'll get going. For some reason, my voice is a bit shot today, so I may not be the loudest person in the entire college again. I guess we'll see. Um, so, um, I sort of mentioned we had the Monday off, so that kind of throws the schedule off a bit. Fortunately, I have a topic that I think I can cover in one day, even including a work period. I'm not going to force it, but we'll see. Um, and that's what we're going to do today. I have no announcements, so I guess, well, other than quizzes are graded, working on the assignment. So that should be posted in the next day or two. There were no surprises. Everyone did well. So there's nothing to say on it. It's generally how it goes in this course, especially early on. Everyone does well. If you hand it in anyway. Last class, we sort of finished our conversation on set theory. We talked about how there's a bunch of rules that we can also use for set operations, for algebra, and that sort of stuff. And then I talked about this Cartesian product, A cross B, which is the set of ordered pairs or tuples for those sets. And then I gave some common examples like R2 and R3, the plane and 3D space respectively. And then there was the quiz. So this is going to seem like we're shifting gears quite a bit, and we are. So I said previously there was a section. Right now, this is when we would start talking about it in previous terms, about proofs. And it follows pretty naturally from set theory. Given the short turnaround time, I have deleted those, and now I'm talking about the next thing, which normally I would talk. So I'd talk about proofs, and then I would talk about a proof technique called induction, which is pretty intimately connected to recursion mathematically. But now that's not there, so we're just going to talk about recursion, so it seems kind of random. But it will fit in with graph theory, I think, talking about graph theory algorithms, because they're generally defined recursively. Actually, most things you run into in the mathematical world as an algorithm and in the business rules world is usually defined recursively, because that's just how people communicate things often. So what is recursion? A function, both mathematically and in programming, is called recursive if, in the definition of the function, it references itself. Of the function, it references itself. So in terms of programming, that means your function will usually return a call to itself, right? So that's what recursion is. And you can kind of see how this would crop up all the time in just business rules, right? Like someone says, okay, do this thing, and now do it on a smaller subset of the thing we just worked on, right? And how do you do that? Well, you just call the same thing you just did on a smaller subset. Now, there is something to note about recursion, and this is getting into the programming part of it. Recursion is easy to implement, with quotes around it, because the algorithm is described recursively, or the business rule is described recursively, so you just read it off and just implement it. But annoying to debug, because your stack gets overloaded with calls to this itself, and you have to unpack it, figure out what went wrong, and inefficient. So it uses a lot of memory when you're doing something recursively, because a function is calling itself and putting itself on the stack, and you're expanding the stack, and it's just kind of bad in that regard. Computer programmers live in the real world, where you have a 2-week sprint, and you're told, hey, implement this thing in 2 weeks, and you look and it's defined recursively, and you're like, oh man, I know how to, if I were given enough time, I could surely come up with a clever way to do that. You do not have enough time though, so you implement it recursively, and then you're stuck with the technical debt of implementing it recursively. But this is just sort of a warning. And every recursive algorithm can be done iteratively. I.e. without recursion. This is another one. This is a math result, not really a compute. Well, it's both. It's both a math result and a computing result. The reason why is because of Turing machines. Do you know what a Turing machine is? Have you heard that in passing? Okay, it's like the fundamental, like, what is a computer in a theoretical sense, and that means it does not have like functions or anything like that. It does not have modern sensibilities for programming, and everything that's described recursively can be done in those. Which means if it doesn't have function calls, that means it can't be recursive, which means you can implement it, which means it does not need recursion. But this is one of those math things where I'm telling you that you can do it. Good luck finding it. Some recursive algorithms are exceptionally difficult to implement iteratively. Some are very easy, though. So unpacking it is sometimes most of the challenge of doing it efficiently. This is all just sort of side stuff. For the purposes of a section on recursion, though, we're going to do everything recursively, right? We're going to do these on purpose, even though finding non-recursive solutions is pretty easy for everything I'm about to present. So, you know, don't worry about the fact that there's an easier way to do this. The point is to demonstrate recursion. So let's start with a first example, which we're going to open with a definition. And that's of the factorial. The factorial of a whole number n is given by, so the notation is n exclamation mark. So this is maybe something you've seen elsewhere. So what this is saying is take n and multiply it by every number that comes before it. So n times n minus 1 times n minus 2 times all the way up to 3 times 2 times 1. Right, so you just multiply all these together. Factorial is one of the fastest growing numbers. So you think like squaring something, that grows pretty big, and then you cube it, that grows kind of big too, and then raising to the power 4, that grows big. We also have exponential, so like 2 to the n grows even faster than those. Factorial grows even faster than this. So when we're talking about algorithm analysis, if someone says, this is O of n factorial, you're like, oh, that's bad, right? That's really, really bad. I think the only thing that grows faster than this is n to the n to the n to the n, like that. It's a weird power tower thing. So anyway, this is bad in terms of computing, but it's still important. It comes up all the time. There are some algorithms that have a best case scenario to our knowledge right now of n factorial. Traveling salesman problem is, I think, one of them. So this is a convention to make our life a lot easier. Notice how I say whole number. For us, we include 0 in that. We just say 0 factorial is 1. Why? Well, there's a deeper theoretical reason why, but it just makes our life easier, and it makes everything make sense. Because like you see right here in this definition, if I said 0 factorial, there's no number that comes before 0, right? So we just need to make a call. Okay, but you see, we're trying to talk about recursion here, and this is not really done recursively, right? If I said, what's 5 factorial, that's 5 times 5 minus 1 is 4 times the next one times the next one, and then we stop, right? So this is not recursive, right? It's just very easily a definition. This is 120, I think. So how are we going to turn this into something recursive? So we can get a recursive algorithm or recursive definition as follows. And this is the simplest case because we can do this very easily without recursion. It's just to give you an idea of how this works. So there are sort of two parts to a recursive function. So the first one is what's called the recursive call or recursive definition. So we're going to say, okay, we've got this function factorial of the whole number n, right? And I checked the course outline. I think in Python you are talking about functions like right now-ish, right? Like it's... Okay, well, this is a mathematical function then. Don't worry about it as a computing function then. So the factorial of the number n is defined as n times the factorial of n minus 1, yeah. So this is what I mean by a function that refers to itself, right? So it says, hey, okay, take our input, and then it's that input times the factorial of 1 less than it. And when it comes to recursive definitions, you can kind of imagine here, let's say we did with this definition, right over here, we've got the factorial of 5. Okay, so we unpack this. This is 5 times the factorial of 5 minus 1, which is 4, right? So I'm being very explicit here. 4. Okay, now we say, all right, well, in order to figure what factorial of 5 is, we need factorial of 4, right? So we say, okay, what's the factorial of 4? That's 4 times the factorial of 3. Okay, now we need that. And you see why recursive definitions are just like this, right? You are calling yourself over and over again, which means you are reducing the problem every time, but you still have to call yourself. This is 3 times factorial of 2. All right, great. Factorial of 2, what's that? 2 times factorial of 1. What's that? Factorial of 1 is 1 times factorial of 0. And what's factorial of 0? It's 0 times factorial of minus 1. And you kind of know the problem here, right? It's going on forever, right? So this is called the recursive step, which is required for something to be a recursive function, but we also need a stopping point, right? We need a base case or a stopping point. So we kind of see here, we were just going to go on forever if we kept following this algorithm, right? But we do have a stopping point. Right here, right? We know that the factorial of 0 is 1. So that means when we got to here, we shouldn't have kept going, right? We should say, no, this is just 1, right? So what we're going to say is the factorial of 1 is also 1. Or sorry, factorial of 0 is 1. That's our stopping point or base case. Okay, so then what does that mean for what just happened over here, right? So this right here was 1. So then that means we follow along this arrow and we say, okay, well this, we just found out, is 1, right? So this is going to be 1 times 1, which is 1. All right, easy enough. So now we go up this arrow again and say, all right, now we know what that is. It's 1. So this is 2 times 1, which is 2. All right, we know this is 2 now, right? We just follow up the arrow, right? We've resolved whatever this was supposed to be. So this is 3 times whatever we just got, 2. So that's 6. And now we continue up. So this is 4 times 3, because that, or sorry, 4 times 6, because that's what we just got, right? We're taking the result that we just found and plugging it in, right? So we're sort of going down this list, and then we get to our stopping point, and we go, okay, now we can go back up and rebuild everything. So this is 24. Yes. So now we go up and we say, the result of factorial of 4 was 24. So this is 5 times 24, which is 120. And that's what we found over here, right? Just from this definition. So this does seem to match the original definition here, right? And this sort of, unpacking and then rebuilding is how recursion works, right? You start at whatever top case you have, and then slowly reference yourself until you shrink the problem down and down and down and down until you get to the smallest possible case, which is the one that you already know the answer to. And then you say, okay, in order to solve my more complicated problem, I broke it down into simpler and simpler problems. And now I solve that very, very, very simple problem. And with that solution, I build my way back up to the more complicated one, right? That's what recursion does. And this is a funny example because this is way worse than this, but it's meant to illustrate what recursion is. An example of a recursive algorithm that looks way nicer in recursion, but is way worse in non-recursive is something called merge sort. It's just a sorting algorithm for computers. The recursive implementation is like very simple, but then if you try to do this, it is like a nightmare. You can look it up on Wikipedia if you want and look up merge sort iterative, and it'll be like, oh God, your eyes will glaze over. It's terrible. So this is just an example. So the point is, in a recursive algorithm or recursive function, in any recursive function, we must always have a recursive step. This makes our big problem smaller. So you're either, dividing an array in half, which shrunk the problem by half. You're reducing the number by 1. Anything like that, right? You have taken something big and made it smaller somehow. Even if it's not that much smaller, you've made it smaller. We also need a stop case or base case. Tells us when to stop. So this is sort of the simplest case that we know how to solve without any effort, right? So if you're sorting a list, well, if you've got an array of 100 numbers, one element from that is already sorted, right? It's sort of the simplest case. Which number comes before 1? 1 is the only number, so it's just by itself. But you can also imagine if you had a list of 2 elements, which number is bigger? Well, you just compare them directly, right? That's sort of the simplest case for sorting a list, right? You've got 2 things. Which one's bigger? Switch them if you need to. Okay, so what are some other recursive functions that we can talk about in math? Well, there's one that is sort of, I would say, quote unquote, common, but it's probably been an exceptionally long time since you've thought about it. And maybe you never even thought of it by name. It's just something that you have done. So another algorithm from math is the greatest common divisor, or GCD. So we first need to remind ourselves, what is the greatest common divisor? the GCD, greatest common divisor, of two numbers often denoted GCD of A comma B, right? It's two numbers, is, well, if you have two numbers, we're looking for the greatest common divisor. Well, these two numbers have common divisors, right? Things that divide both of them evenly. We're asking for the biggest one amongst that list, right? That's all the GCD is. The greatest divisor of both numbers. And this is one of those things when you write it in words, you're like, but then when you actually, put it on the board, it's a lot easier to see. So let's just do it with an example. I have to draw a Venn diagram, so hopefully I have enough space. Find the GCD of 12 and 42. So our goal is to say GCD of 12 and 42 is what? So the naive way to do this without any sort of algorithm is to just ask ourselves, okay, let's list out all the divisors of 12 and all the divisors of 42 and see which one's the bigger one in common, right? Okay, so list divisors. So divisor, again, remember, means evenly divides the number. For 12 and 42, take biggest. So we've got, oh, that's not enough space. Weird egg-shaped circle now. So divisors of 12 on the left and divisors of 42 on the right. So, okay, divisors of 12, pretty easy to come up with. What are the things that evenly divide 12? I think I heard all of them across the room, yeah. 4, 6, and 12, right? Those are all the things that evenly divide 12, right? What about 42? 1 and 42. So the easiest way to do this is to kind of build a factor tree. So you've got 42 here, 2 and 21, 7 and 3. So that means 2, 3, and 7 are in there. 14, 21 are in there. And I think that's everything. Oh, 6. Okay, great. Now, what we do is we just move the ones they have in common into the middle, right? They both got 1 in common. They have 2 in common. They have 3 in common. They don't have 4 in common. They do have 6 in common. Actually, this should also mean yeah. I think that's it. Yeah, because 12 does not divide 42. Okay, great. So now we just look at this and we say, well, what's the biggest one? Easy. 6. So the GCD of these two numbers is 6, right? Now, I don't think it takes too much analysis to say this is a bad way to do it, right? Because now, instead, suppose I asked you to find the GCD of 1,262, and I'm just gonna, I don't know, a big number, right? Who cares, right? Big number. So what's the GCD of this? Well, if we were to follow this technique, okay, first list all the divisors of 1,262, and then list all the divisors of whatever that is, right? That seems bad for many reasons. One, that's going to be a huge list that you probably don't need. And how do you know you found all of them, right? Like this one's pretty straightforward because we can build the factor trees, right? Like you got 12, and it breaks down as 4 times 3, and that's 2 times 2. So, okay, you can build up all the factors from factor trees, right? But this number and this number is going to have a very big factor tree, potentially. I mean, maybe it doesn't. Who knows, right? If this is a prime number, then, it would be 1 and that. I mean, it's not going to be because of the 2, but there. Now maybe it's a prime number. Who knows, right? I don't know. So, it's an inefficient way of doing it. So we want to find a better way. And this may be something you did in high school. Some of you, probably not. There is a way for finding the greatest common divisor. And it's called the Euclidean algorithm. Does that ring a bell? Has anyone heard that one? No? Okay, that's fine. I usually don't expect anyone to have heard of it unless you took discrete math in high school, in which case you're nerdy like me, which is fine. So there is a better way. This is called the Euclidean algorithm. And the reason why it works is kind of a whole conversation on its own. It would take several days of talking and defining stuff, and I don't know if you want to hear it. So the point is, we can recursively calculate the GCD. So the Euclidean algorithm is given by, and it's not going to seem very mathy because I'm going to write it with words. So it's a recursive algorithm, which means we have a sort of ending point. So if the second number is 0, then we just say, okay, well, the result is A, right? The greatest common divisor of A and 0 is A, because everything divides 0 evenly, because 0 divided by any number is 0, right? No matter what, so everything divides 0. So then the biggest number that divides 0 and also A has to be A, right? Because literally every number works here. So the biggest one has to be A. So this is our stopping point. Now, when we're looking at something recursive, this number, if we want it to eventually get to 0, better get smaller, right? We want that to get smaller, so we're shrinking our problem. So the GCD of any two numbers. So what we do is we take this number and we shift it over. And I want to make sure I write this down. This second number, I'm going to put it in words because there's no easy way to put it in symbols. The remainder. Okay, so you have talked about modulo. Okay, good. Then, yes, there is an easier way to write this. A modulo B. So it's the remainder of A divided by B. So I'm still going to write that in words because that means you have talked about various operators in Python. So the remainder of A divided by B. So this definitely shrinks that second number, right? Because when we the remainder of 12 divided by anything is at most 12, but it will get smaller, right? It's actually strictly less than 12, between 0 and 11. So this number will definitely get smaller. Maybe it gets small really slow. Turns out no, the Euclidean algorithm shrinks very quickly. Like even for really big numbers, this would probably be like 3 or 4 steps. Actually, like it's really not that many, unless you get exceptionally unlucky. So there is a worst case behavior for this algorithm. It's very specific. Have you heard of Fibonacci numbers, like just cultural osmosis? Those are the worst case scenarios. So if you take 2 consecutive Fibonacci numbers, then this algorithm it just breaks down. It still works, but it's funny because if you have 2 Fibonacci numbers, the GCD is always 1, but it's still going to go through literally every single number in the Fibonacci sequence. So it's bad. But most of the time, it's very quick. Most of the time, it goes quick. So let's go back to this, right? I think based on just listing all of these out, right? Do we agree that this is 6? Right? We've listed out all the divisors here, and this is the biggest one they have in common, right? So I think we're probably safe to say this is 6. This answer is 6. So if I'm claiming this matches this, then it better be 6 when we do this algorithm on 12 and 42, right? Okay, well, we're not going to do that. So let's try on 12 and 42. So the GCD of 12 and 42. Okay, so what we need to do is move the second number to the first spot. And then figure out A percent B, which in this case is 12 divided by 42. What's the remainder? It's 12 in this case. So this is an interesting thing about this algorithm, and this sometimes happens. We want to start with the biggest number in the first spot. So because we look at this and we're saying, oh, we're going to divide a number by a smaller number, presumably, right? So we want the bigger number to be there, but this algorithm fixes itself if you don't, right? It just shuffles them. So anyway, this is 12 because 42 fits into 12 0 times, and then there's 12 left over. Now we rinse and repeat. We have to figure out this number. So this is 42 modulo 12. So 12, 24, 36. What's left over? 6. Okay, great. GCD of 6 and 2. Sorry. 6, and now we have to do this. 12 divided by 6. What's the remainder? Yeah, there's no remainder at all, right? We're in our stopping case, right? This is saying, hey, when we're here, when the second number is 0, just spit out the first number, right? And we're done. And that matches what we did when we listed everything out, right? But you can kind of see that if you did it with those really big numbers, it doesn't really matter, right? This algorithm is going to work the same regardless of how big those numbers are. So that's pretty nice. So I also have one more example. It's basically invented just to practice with more recursion. But the thing is, I'm just giving you a taste of this. In later homeworks, I'll have you explore more interesting algorithms. It's just the problem is when we're early on, we don't have any topics we've covered that are interesting enough that use this stuff. And some of the stuff I would want to talk about are heavier on the programming, so I have to wait, right? It would be pretty unfair to me to just be like, all right, let's talk about, you know, this merge sort, which uses a bunch of object-oriented programming principles, and you'd be like, well, Travis, what the hell are you talking about? So it's like, okay, I have to wait until you've covered that. So the stuff we're talking about here is like elementary or like constructed specifically to practice with recursion. But I do promise we will talk about more interesting recursive algorithms. Specifically, they'll probably come out of graph theory and some of the matrix stuff. Okay, so define a function as, so this is, I made this up literally before class. Like it's what's it used for? This example. So f of n 0. So when that second number is 0, that's what this means. We're going to say, hey, it's minus 1, right? We also have, so this is a second condition, which is totally fine. We can have as many stopping conditions for recursive algorithms as we want. And it's saying if the first two numbers are the same, right? That's what n comma n means. They're the same thing. Then we're going to say, hey, that's 2. Right? Just random, arbitrary, made up. Okay, but what do we do? So this is the sort of stop. But what about the recursive step? Well, we have two numbers here, so I have to call them something different. Right now, this means they're different. That's important. So we shrink the first number by 1 and the second number by 1. Minus 2 times, we're going to call it again, like this. So this notation can sometimes be a lot to unpack, but when you start writing functions, you're just going to get used to it. This is if you implemented this in Python, it would look almost exactly like this, right? Okay, so let's use this to compute f of 3, 2. So we're essentially calling this with these parameters. All right, well, we just go through the motions. So I'm going to use colors here. Is anyone here colorblind? There's usually someone who is, so I just have to ask. My colors are never required to see. It's just I'm using them for emphasis. So I ask if someone's like, I'm red-green colorblind. I'd be like, okay, I won't use red and green then. So we've got these numbers, 3 and 2. So what does this function do? It says, okay, it's 3 times f of, well, we're going to shrink it. It's 3 minus 1 and 2 minus 1. So this would be 2 and 1, right? Those are our inputs. Minus 2 times f of, again, 3 minus 1 and 2. Right, so this is me kind of showing you where everything is going along this, right? So again, this is now 2 and 2. Okay, in order to figure this out, we need to figure out these smaller parts, right? We've broken our problem down into smaller parts. So let's figure out, this right here is f of 2, 1. So we need to figure that. F of 2, 1. What's that? Well, our second number isn't 0, and the two numbers aren't the same, so we break it down again. 3 times f of 2 minus 1. And 1 minus 1, f of 2 minus 1, and 1. Okay, so again, I'm writing down these minus signs in here. You can do them in your head if you want. I'm just doing it for illustration. So this is f of 1, 0, f of 1, 1. Great. Those are our base cases, right? That's our stopping points. So this, we know, right here, is minus 1. And this right here, we know is 2. So, okay, that means this is 3 times our minus 1 minus 2 times, we got a 2. Okay, cool. So that's minus 3 minus 4 minus 7. We got a number. Okay, cool. That means we figured out what this piece is. Right, so this thing is minus 7. Cool. So now over here, we've got 3 times this minus 7 minus 2 times that. Well, we have to figure this one out too, right? But this right here is 2 comma 2. Those two numbers are the same. So we're in this stopping case, so we know, that's just 2, right? So this is 2, and we can finally say this is minus 21, minus 4 is minus 25. So then this recursive function is minus 25. So f of 3 comma 2 is minus 25. So again, this is constructed specifically to do this. It's not a useful function. It's just to get you in the habit of like thinking about what recursive functions are and what recursive definitions are, and just sort of going through the motions, right? Just kind of tracing your steps, unpacking things, being careful, and then getting to the lowest case and then building it back up. Yep.
And the second one, when it's at the top, minus 2 times function of 3 minus 1 and 2.
This?
That 2, that's not 2 minus 1 or anything like that?
This one?
Yeah.
Yeah. No, because the function here says it's f of, take the first number minus 1, and then just plug in the second number.
Gotcha.
Yeah. So that's why we have 2 here. So I was writing in the black the stuff that is just part of the original definition. The only thing that's changing are these numbers, which I guess this should be also in black. Yeah.
The second function on the right side of the equation in the first step hadn't satisfied either of the rules. Would you have to do the whole thing again?
Yes. However, you often end up with duplicate work. So what I mean by that is, let's say instead this was f of n minus 1 k minus 1 or something like that. Then you would often find yourself looking, like, you'd go through this first bit, and then you'd start going through this, and you'd be like, hey, wait, I already did this, right? Like, you would see this would be 2 comma 1. Oh, wait, we already did that, so I just plug it in, right? So you wouldn't need to redo it. This, though, is partially why recursive algorithms are bad, depending on the programming language / compiler, is you just did this. Your computer doesn't know that. So it sees this, and it does it again. So it just duplicated work, which is why so modern compilers can kind of detect that you're doing that recursively, and it'll be like, hey, we already did that work. We don't have to do it again. They're a little smarter about it. But yeah, you can often save yourself effort by just using the work over again. Any questions? Feeling okay? I just wanted to give a brief introduction to this, and this is the part where I would show you how to implement these in Python. But if you haven't talked about functions yet, I don't know if I should do that, but I can still show you if you want. Okay. So I checked the course outline and it said, functions this week. And I was like, oh, that lines up perfectly.
Maybe tomorrow.
Yeah, like this is probably going to be one of those things where it's just the way the term schedule worked out.
Yeah.
So you're going to like go into class tomorrow and you're like, oh, Travis kind of already showed us a bit of functions on, but I'm not teaching you functions. I'm just showing you stuff. They'll teach you functions tomorrow, probably. If not, I'll ask on Monday, did you cover it? Because if the answer is still no, I'll be like, okay, then I definitely need to move this later. Because I covered it today because I was like, the schedule seems to say it would work out. But anyway, let's do the GCD as an example here. So when you want to define your own function in Python, you
might want to put the screen down.
hey, that would be a great idea. Look at me, I'm so smart, and also I should make it bigger and turn the lights off. You can tell I'm a math guy because I never use the projector. Like it's not something I do very often. Okay, so when don't worry too much about this. Like I said, your instructor is going to talk about it. So this is how you define your own function in Python. So let's just think about what our GCD algorithm did. It said if that second number is 0, then we just return the first number, right? So if b is 0, then what are we going to do? We're going to return a. So return just means, hey, give that back, yeah?
Is there a way you can zoom that in?
I can zoom it in pretty far, probably. Is that better?
Yeah.
Okay, perfect. I can't go any further because then it gets rid of the output, but I mean, I guess we would deal with it. So otherwise, if that second number is not 0, then we need to do our recursive call. So this is the part where we're going to say, hey, the definition referenced itself, right? So what did it say? It said, well, do the GCD of b and a modulo b, right? But the thing here is we need to actually return this just for function reasons. Okay, so now we should be able to say, all right, give me the GCD of, what was it, 12 and 42. And if I didn't write a syntax, oh, right, I have to print it. Oops, nope. Look, this is hard to type on the... So 6, right? So that's what we got. But now let's see, let's do big numbers. 1 instantly, right? We can actually this is inefficient, but we can see what these are. Let's see this step. Let's just see how many it ran, right? We don't need to see the number. Let's see how many steps it did. That's a lot, but it's not that many considering how big these numbers are, right? Like it's I don't know, like 10 or 15 steps of this. So you wouldn't want to do this by hand, but even if you did, it would take you like 5 minutes, right? That's how efficient this algorithm is. So yeah, it's pretty nice. Yeah, anyway, this was just me showing you that like the nice thing about recursion in programming is this is like 5 lines, right? And you know, you could shrink it down. There you go. Now it'll be even less if you really want to. If you really want to play Python golf. But like, it's really simple to implement, right? And that's true of all, like that, this invented one I just made right here. we can also implement it exactly the same way, right? When you have a recursive algorithm just sort of given to you, programming it is very easy, but it's inefficient. So you should avoid it unless you have no choice, which in the real world, when you're working, you usually have no choice because your boss said, do this in a week. And you're like, well, the good solution would take me several. So you get the one that gets it done in a week, which is very common. Okay, so with that, I have what I'm going to call a quote-unquote simple quiz. When you're first working out with recursion, none of them are simple. It just takes a lot of brain power and effort to understand recursion. But it's basically this. I took this and just changed it very slightly. So you can use this as reference for the quiz is kind of what I'm getting at. I want to keep it similar to almost identical to the example we did.